Welcome to the Volume of Revolution Disk Method podcast. I think I have about five slides here, and then I'll give you the closing. So we want to find the volume of the solid formed by revolving the region bound by f of x equals 2 minus x squared and g of x equals 1 about the line y equals 1. All right, so here it doesn't, notice that g of x, I'm going to kind of point out here that g of x equals 1 and about the line y equals 1 is the same thing. Right? These don't have holes in them, right? So I don't have to account for the y equals 1. I'm going to account for it as part of my function, g of x equals 1. So first of all, we have to find where these two graphs intersect. And to do that, we're just going to set them equal to one another. Right? So 2 minus x squared equals 1. I'm going to move everything to the right-hand side. 0 equals, I'll have a positive x squared because I'm going to add x squared to both sides. And I'm going to subtract 2, so it'll be a minus 1. This factors to x minus 1, x plus 1. So my two solutions here are x equals 1, x equals negative 1. That's my interval. When I set this up, you can see from our picture here that on top we have the graph of 2 minus x squared, and on the bottom there, I'm writing it in blue here, we have the graph of g of x equals 1. Right? So that's the region, and we're creating this eggy shaped thing. When you're using the disk method and you've got two functions, you don't need to worry about right when it's the x-axis, right? Because then that would just be x equals 0. Why would you subtract 0? But for x equals 1, we're just going to subtract 1. And if you have two functions, you're rotating around something else that's besides the x-axis that's creating your solid of revolution here. You're going to get your radius. Your radius is equal to upper minus lower. Right? So the upper function is the 2 minus x squared. The lower function is the 1. So my radius is going to be 2 minus x squared minus 1. So that's going to give me, if I subtract 1, I have 1 minus x squared. That's my radius. Right? So I've got these disks here that we're revolving. Imagine them to be cylinders with really super skinny width. Right, and the yellow cylinder's drawn in there. So this radius here, this r, is just 1 minus x squared. Right, and we use the area of a circle. The area of the circle, remember, is pi r squared. So to find the area of the base, I'm just going to take my radius, substitute it for r, multiply it by pi, and square and multiply by pi. And then, because it's actually a really skinny little cylinder, I need my change in x. Change in x is dx. Right? And then we're going to integrate that. When we integrate that, we're summing up all the little disks, all the little skinny little cylinders. And that's going to give us the volume of our solid. Right? So to solve this, we're just going to integrate. And I need to square. So my radius is going to be 1 minus x squared. I'm going to just pull the pi out right off from the beginning. And this is being integrated from negative 1 to 1. So now we'll just square that, and then we can integrate. So this is my volume. Volume equals pi times the integral from negative 1 to 1. If I square that, that's going to be 1 minus 2x squared, right? Because I'll have 1 times negative x squared and 1 times negative x squared, and then plus an x to the 4th. Right? I figured it was okay if I just squared it sort of in my head and not write down all four products. But when we square it, we'll get 1 minus 2x squared plus x to the 4th. And now we're just going to integrate that. So our volume is going to be, did I include my pi? Yes, I did. Pi times, and then we'll have x, and that'd be minus 2x cubed divided by 3, and then plus x to the 5th divided by 5, and we're integrating that from negative 1 to 1. I'm going to try and squeeze it in here. I really would like a little, I can't really stretch here because my microphone only reaches so far. So our volume, and I need to explain the parentheses, our volume is pi times, and we'd have, I'll try and squeeze it in here, 1 minus 2 times 1 cubed divided by 3 plus 1 to the 5th divided by 5. And then subtract from that the same thing, but we're going to get -1. So we'll have -1 minus 2 times -1. Oops. That looks like now like a -11. -1 cubed divided by 3 plus -1 to the 5th divided by 5. Right, I'm going to have to start writing up here a little bit. So I'm just kind of continuing up there. So our volume is, so that's going to be 1 minus, oh, don't forget my pi. Guess I should put my marker down when I erase. There we go. So we're going to have, our volume is pi times, I've got 1 minus 2/3 plus 1/5 minus, and that's -1. That's going to be plus 2/3 because I'm going to have a negative and then I have a plus there, so it'd be a plus 2/3. And then this would be a minus 1/5. All right, so our volume is going to be pi, and it looks like we have some things, some of it canceling out. Not really. Let's just kind of add these things like things together. So I've got 1 minus a -1, right? So that's going to be 2. Everyone okay with that? I've got -2/3 minus 2/3. So that's going to be minus 4/3. And then I've got 1/5, and I'm subtracting a negative, so that's going to be 2/5. And so now all I need is a common denominator, then I can add these things together. 15 is going to be the common denominator. So I'm sorry, I have to squeeze this in a little bit. So our volume is pi times 30 minus, so 5 times 4 would be 20, and then plus 6 all over 15s. Right? Everyone sees I'm just changing 4, like, so -4/3 is -20/15, and 6/15 is 2/5, and so forth. So that's going to give me 16/15. So our volume is 16/15 pi. There it is. We are done. All right, so not too difficult. Even the evaluating wasn't too difficult because I had a lot of 1s and -1s. So I hope you can follow that. I post this, I may have to move my writing down, or it might get confusing for you. I don't know. All right, let's go on to the next one. And of course, if you have questions, ask me in class. All right, here we're going to we have the equation y equals x squared revolves about the x-axis. So here we have to graph it first. So just, and I don't care about the negative side, so I've got half a curve. This is just showing you our disk here, so of course it's going to rotate like that. This will be the radius, so the radius is just the distance between the x-axis and the function there. Right? So my radius is x squared. We've already told we're evaluating it from 0 to 2, so we already know the interval here. And notice it says it'd be easily solved with the disk method. We know that because the graph touches the axis of revolution. If it doesn't touch the axis of revolution, we'll have a hole, and we'll learn the washer, and we'll use the washer method, which we'll learn in the next lesson. All right, so let's just set this up. Remember, area of a circle is pi r squared, and our volume is going to be the integral for pi r squared dx, right? Because we have a change in x. This is all that's our width. The dx is the width, right? Because these are teeny little cylinders. All right, so our volume is going to be pi times the integral from 0 to 2, and my radius is x squared, so I'm going to square x squared dx. So that's going to give us pi, and then evaluate it from 0 to 2 of x to the 4th dx. So that volume is going to be pi x to the 5th divided by 5, evaluated from 0 to 2, and then we just plug in. So the volume is, and the 0, notice, is not going to matter. It's going to be minus, but I'll put it in pi, and then I'll have 2 to the 5th divided by 5, and then this would be minus 0, right? Because it's going to be 0 to the 5th, which is 0. And so that's going to be 32 fifths. So our volume here is 32 fifths pi. And then we're done. This was a pretty easy one, I think. Hopefully you thought so too. We need to do a couple around the y-axis. So revolving about the y-axis, so find the volume of the solid formed by revolving the region bound by f of x equals x squared about the y-axis, excuse me, from 0 to 4. All right, so normally, right, we wouldn't solve the x squared, we wouldn't take the square root. However, notice that we're revolving it. So if I revolve the square root of x, I'm going to have the same thing as if I revolved if I revolved y equals x squared, right? Because that's just going to be, you know, the revolving portion of the y equals the square root of x equals the square root of y was going to go exactly where x squared would go. You know, so whether I have, either way, I'm going to have the exact same shape, right? And since we're revolving around something vertical, it has to be a dy. Anytime it's a vertical line, it has to be a dy. All right, so we're going to isolate. We have a vertical line. We solve for x. So if y is x squared, take the square root of both sides. You can only, this is something you would use this for, right? If we were finding the area, that would be different, and we wouldn't be using it this way. We would have different cross sections. So we have, we wouldn't be revolving, would we? So we have the square root of y equal x equals the square root of y. Now make sure that your it says notice it says x from 0 to 4. If you're integrating with respect to y, you want y, right? So you need y. So how do you find y? Yeah, just plug it in. So if x is 0, right? So this is from 0 to 4, that's what x is. So y would just be 0 squared, right? So y is going to be 0 squared, which is 0, to 4 squared, which is 16. So we're going to be integrating that from 0 to 16. Make sure it matches. That was a test to make sure you knew, hey, don't use the x values, you need the y values. You need y values if you're revolving around a vertical, and you use dy. Other than that, this is a pretty straightforward problem. All right, so my radius is the square root of y. I have to square my function. That's the distance with our, and you can see that nice little disk there drawn very nicely. That would be the function is what creates our radius. So from the in this case the y-axis to the function is our radius. And then the thickness of that is dx, because we're moving along the x-axis. This time we're just moving vertically. All right, so we have the square root of y squared, and we're going to be evaluating that from 0 to 16. Don't forget your pi. You'll get, on the FRQs, you'll get a point just probably for remembering the pi in this thing, because these are disks, right? And so it's a circle, and we need a pi. So y squared is, the square root of y squared is just y. And so we integrate that. We have pi times y squared divided by 2 from 0 to 16, and you plug in. Of course, the 0 won't make a bit of difference, and 16 squared divided by 2 would give us 128. So our volume is 128 pi. I think a really straightforward problem. The only tricky thing is using y as your limits and rewriting this in terms of x. Other than that, I think this was a real straightforward problem. All right, here's another one with respect to y. I left the graph up here since it was actually drawn pretty nicely by me. My line's actually straight. We want to find the volume of the solid obtained by rotating the region between x equals 2x minus 4 and the y-axis, which is x equals 0, about the y-axis from y equals 2 to y equals 6. All right, so we're going around the y-axis, right? So our disk, and it's from 2 to 6. We already know our y's, which is good. We have a problem if we go below 2, right? This won't be, we couldn't use the disk method anymore because we wouldn't be on caught my bracelet. We wouldn't be touching our axis. So basically what our figure kind of looks like, try and draw this. So we're revolving it around here. We'll have another side over here. So it's kind of this cone shape from the line revolving, because the other part of the line won't matter because it's only from 2 to 6. All right, so we have our limit. We're given our limits of integration. They're y's because it's a dy. Our equation, though, is solved for y, not x, so we need to solve it for x. So you'll add 4 to both sides and divide by 2. So 1/2 y plus 2 is your equation. Remember, you have to square it because it's pi r squared for the area of the circle there, and then dy for the thickness. So if we square 1/2 y plus 2, we get 1/4 y squared plus 2y plus 4, and then we just integrate that. So that's going to be 1/12 y cubed plus 4, so we increase it by 1, right, and we divide. So we'd be increasing the exponent to 3 and dividing by 3. So we have 1/12 y cubed plus y squared plus 4y evaluated from 2 to 6. So now we just plug in the values, right? Plug in the 6 into all of them and then subtract all the 2, plug in the 2 and subtract that from the 6's, and we get as our, and you can look at that. I don't think you'll have any issue with the steps there, how to get some common denominators, but our volume is 260 pi fourths. That would be our volume, that would be a cone. All right, so now let's look at our, I think this might be our last one. No, it's our second to last one. Here's another one rotating about the y-axis. We have x squared from 0 to 4. Kind of, 0 to 4 on the y, wait. Yes, 0 to 4 on the y, all right. So this one actually is almost identical to the one I drew. So it's from 0 to 4 instead of 0 to 16 because they're given the y values. If x is 0, y is 0 too. So here, almost the same problem. I don't think there's really issue with this one. Shame I chose some that are so similar. Should have chosen something different. So this would be y, right? dy, and when we integrate it, that's just going to be y squared divided by 2, and you evaluate it from 0 to 4. And why is there an 8? Oh, because a 2 is there. Oh, I forgot about the 2. Almost, I'm looking at that. Why is it 8 pi, not 16 pi? Because there's a divided by 2. So our volume we would just plug in. We'd have 4 squared divided by 2 times pi, and of course that's 8 pi. So I think this one is even more straightforward than the other one. I gotta replace this problem. You could put in a harder problem. But it's already in there, and it's probably in your notes. This is the last one, and this one's about the x-axis. And I could always do another one about the y-axis or a vertical line. I notice I don't have one about another vertical line. Maybe I should do one like that. So I'm going to add a problem. I'm going to have 2 podcasts. One with one problem. I have to write the problem down. Something around a vertical line that's not the y-axis. This one was about the x-axis. Let's draw this one. All right, so there's my graph. I want to graph it. So I've got 3x minus x squared. All right, I'll just factor out an x, right? And so I'll have 3 minus x. So to graph this, I have an x-intercept. My 2 x-intercepts are 0, 0. And if I have x minus 3 equals 0, then I'll have negative x equals negative 3. So 3, 0. So those are my x-intercepts. So I'm going to graph this. So 0, 0, and 1, 2, 3. 3, 0. It is an upside down, concave down parabola. It's not really that important where my vertex is, so I'm not going to bother finding it. Of course, well, the x value is at 1.5. It's really not important where the y value is. That's good enough for our graph. So of course, when it revolves, it's going to kind of look like that. There it goes. All right, and so here would be our. Here's my disk there, my sample disk, and my radius would be that, right? So my r is just going to be the distance to the x-axis, from my curve to the x-axis. So my r is going to be 3x minus x squared, of course. All right, so we are already given from 0 to 3, which works out pretty nicely because that's where it intersects. Therefore, that's all we could do is from 0 to 3. Well, we could do less. We could do from 0 to 2, have a different shape, but we couldn't do anything more than 3. So now I'm just going to integrate. So we've got pi times the integral from 0 to 3. We have 3x minus x squared all squared dx. So that's going to give us pi integral of 0 to 3. I had to square that. That's going to be, I'm going to try to square it in my head. It's going to be 9x squared. And then I'm going to have minus 6x, right? Because I'd have a negative, or 6x cubed. I'd have a 3x times a negative x and a 3x times a negative x. That'd give me negative 6x cubed. And then plus x to the 4th dx, if I can reach. All right, so now we'll integrate that. So this would just be pi times, I'll have 9x cubed divided by 3 minus 6x to the 4th divided by 4 plus x to the 5th divided by 5. And we'll evaluate that from 0 to 3. All right, so we'll have, I'm going to simplify that. We'll have, and that's our volume. I probably should put V. So V equals pi times 3x cubed minus 3x to the 4th divided by 2 plus x to the 5th divided by 5. Come on, erase. I have to remember to put the pen down and then pick up the eraser. X to the 5th divided by 5. And that's from 0 to 3. Of course, the 0 is not going to matter. So we have pi times 3 times 3 cubed minus 3 times 3 to the 4th divided by 2 plus 3 to the 5th divided by 5, and then minus 0, right? Because that's all it's going to be when I plug in a 0. So that's going to give me 81 minus 3 to the 4th is 81 times 3 would be negative 2, would be 243 halves. And 3 to the 5th is 243 divided by 5. So I just need a common denominator here, which would be 10. So we have pi times, I'll have 810 minus 243 times 5. There's a calculator way over there. I'm going to grab it. After tutoring, sometimes I just don't want to have to multiply everything in my head. So 243 times 5 is going to give me 1215. 1215. And then this would just be 486. And those are all over a denominator of 10. Just a little easier there. And so that's going to be, I'm going to use that calculator again. So 810 minus 1215 plus 486, 81 tenths, or 8.1, whichever you like. So either 81 tenths pi or 8.1 pi, whichever you like. All right, and that's all there is to that problem. All right, so Let me know if you have questions, and maybe I'll try and scroll up so you can see the whole problem. If I didn't write so big, I wouldn't have needed so much space. There we go. So let me know if you have any questions there. Oh, you can almost see the whole thing. Just can't see the bottom. Actually, if I started a little higher, I'll just drag the rest of that up there so it all squeezes in on one page when I post it. All right, so I'm going to end this podcast, and if you see another podcast, it means I did one more. Actually, I am going to do one more problem, but I'll show you the closing first, just in case. Let me show you the closing, and I'll show you again in the next podcast. So the closing for Wednesday is to sketch the solid attained by revolving the region under the graph of f of x about the x-axis over the given interval. So I tried to keep it nice and simple for you on a closing. F of x equals x plus 1 from 0 to 3. So make sure you graph it, write down where your sample disk is, and then remember you'll find your radius, and you just plug that in for our formula for the volume of the disks, each disk, and then integrate to find all of the disks all together in the volume of this figure. All right, so I think this is a fairly straightforward problem. I tried to keep it kind of simple for you on a closing. All right, so I think I'll probably see you in the next podcast, because I think I want to do one more with a revolving around a vertical line, not the y-axis. So stay tuned for that one. All right, bye.